All right, so today we will start talking about magnetic materials and their properties. And the key concept that we need to introduce to adequately model magnetic materials, or another way of saying it, how the medium. Remember, we said in electromagnetic theory, one big portion of the theory is dedicated to describing or modeling the medium. So we know how the medium reacts to the electric field. The question is now, how does the medium react to the magnetic field that we quantify using the vectors B, H, and A? Okay, so the study of how the medium reacts to the magnetic fields is how we define the properties of magnetic fields, of magnetic mediums or magnetic materials. And in the same way as in the electric case, the cornerstone was the dipole, right? So we defined the dipole, which we can write in different ways, draw different ways, right? And I could draw it like this. Right? So I have a positive charge, negative charge, and a distance d between them, right? So in the same manner where the electrical dipole was the tool that we utilized to model the medium or the material and how it reacts to electrical fields. The magnetic dipole in this case, something called the magnetic dipole, that's what will be the tool. That is the tool that we will use to describe magnetic fields, magnetic mediums, to model magnetic mediums. Okay, so that should be step one. Defining the magnetic dipole. What is the magnetic dipole and how does it relate to the electrical dipole? The concept in magnetism that is, ultimately we took the electrical dipole and we used it to define polarization. Right? In the same manner, we will take the magnetic dipole. I won't draw it now. Just the M dipole, right? And we'll use it to describe something called magnetization. And magnetization and polarizations are analogs of each other. So let me give you kind of the big picture. And this big picture will be useful in understanding Maxwell's equations and the motivation for writing Maxwell's equation, which is the complete picture, So the motivation for writing Maxwell's equations the way they are, right? So this is the big picture. Okay, so in the case of E and D, fields, the electrostatic fields, we described the effect. We modeled the medium as swimming, or we modeled the medium as having a bunch of dipoles that are attached to the medium. They are stitched to the medium. And they orient and they react to the electric field. So they react to the electric field density by orienting themselves, stretching or contracting, and so on and so forth, right? And they are the root cause for permittivity to our eyes. And we derived all those formulas, right? And then one dipole here looks something like this. It's just Q plus Q electrical charge, Q minus QE minus, and then a distance between them, D. That's the dipole, and it's a bound charge. It's a bound charge, meaning it's cannot move in space. It cannot move from one point in space to the other. It remains where it lives, and the only thing it can do is it can stretch and orient itself. Okay, there's an alternate picture. There's an alternate mathematical picture for describing the electrical dipole, by the way. which is we can describe it as a bunch of loops of current. Loops of current that, again, they are bound currents, meaning they do not, so they are bound currents, right? Meaning they do not move from one point to another in space. They remain in their point in space. But what they can do is that they can change their orientation, and the magnitude of the current can vary. So they can change their orientation, the magnitude of the current can vary, and the diameter of the loop can vary. So this is an alternate mathematical model for describing the same thing. It will give us the same analogous equations as the dipole looked at as two charges with a distance between them. There's one piece of information I still haven't given you, which is those are not currents of electrical charges. Those are currents of magnetic charges. So those are bound magnetic currents, meaning that the current, if I zoom in on a dipole here, I have a loop, I have a current, but the current is a magnetic current, meaning the charges moving in this tiny filament, has a radius of d, are magnetic charges. The same kind of charges that we said don't exist in nature, but they exist in the mathematics, and we can easily imagine them to exist. Right? So this is an alternate way of describing the same electrical dipoles. Okay. Now, what about magnetic dipoles for the H and B field? Right. So we can, for the electrical dipoles, we can say that the E field affects the medium by affecting the dipoles, and the dipoles could have loop form or this form where they have two charges with a distance between them, right? And in the dipole form, in this form, they're just two electrical charges with a distance between them. In the loop form, they are tiny loops of magnetic current, the kind of current that's the movement of magnetic charges, which we do not exist in nature, but mathematically can exist. They exist in the mathematics. All right. In the same way, we can examine the magnetic field and say, hey, there are two kinds of dipoles. We can describe two kinds of dipoles in the magnetic field. We can describe the kind that are two charges with a distance between them that's spread all over all of space or the medium, and those are bound. Those are bound magnetic dipoles. And they are constituted from, if we zoom on one, they're something like this, and then the charge is Qm plus and Qm minus. I can draw it like this. So those are two magnetic charges with a distance between them. Here the charges have units of Coulomb. Here the magnetic charges have units of Weber. We said Weber describes the magnetic charge. So this is one picture, and this is a valid picture for describing dipoles in magnetism and describing the bound dipoles that exist in magnetism, and they can be used to devise a sort of a polarization for magnetic fields, and we can use that to describe the properties of the material, right? But then also there's the alternate picture where we can look at dipoles as loops, tiny loops. Now in this case, in the same way where we went from two charges with a distance between each other to magnetic current, here we go from two magnetic charges with a distance between them to electrical current. So if I zoom in into one of those loops, so those are bound electrical currents. Right? If we zoom into one of those loops, it's a loop like this, and it has a certain current, it has a certain distance. Right? And then this is a dipole, and the dipole is determined by the diameter and the amount of current. And this dipole orients itself with respect to the magnetic field, interacts with the magnetic field. Okay, So those are the four alternate ways of describing dipoles. For physical reasons, for reasons where, because we know from our study of nature, although the mathematics allows it, we know from our study of nature that magnetic charges, this sort of thing, and magnetic currents don't exist. So historically, it was chosen to describe dipoles. It's not the only correct way. What I'm trying to push is that it's not the only correct way of describing dipoles. It's the way that people settled at, right? Because they are. It's the picture that matches classical reality the most. Okay. Of course, in more advanced theories, magnetic charges and magnetic currents are assumed to exist, of course, and under certain conditions, they might exist, but that's beyond the scope of this lecture. But in classical theory, the choice for describing dipoles is this. And we choose those two ways of describing dipoles because those are the two ways that mirror what exists in nature, at least classically. Okay, so we describe the medium and its effect. We describe how the medium is affected by electric fields by imagining electrical dipoles embedded in the medium, and we describe the effect on the medium from magnetic fields by imagining electrical loops of current existing in the medium. We have to, because if we do it any other way, we will have to imagine things that we know don't exist in nature. That's why the description of the dipole in magnetism is different than the classical traditional description of the dipole. That's why the classical traditional description of the dipole in magnetism is different than the one we used for electrostatics. We used two charges for one, and then we use loops of current for the other. Okay, so and yeah, this magnetic dipole is the building block for modeling materials in the same way that the electrical dipole was the building block for describing different kinds of materials in electrostatic, mainly dielectrics. All right, so we have to start with the magnetic dipole. Okay, and this is mainly what's used to model magnetization in the medium. So you can, if you can want to guess, what will happen is we will study an individual magnetic dipole, and then we will imagine an infinite amount of them embedded into space, and they cannot move. They are bound magnetic dipoles, and they just orient themselves and increase in magnitude. They could expand, the current could increase, right, in reaction to the magnetic field. Okay. So let's set up our study of the dipole, magnetic dipole. So as always, we need a coordinate axis, x, y, z, and then the loop, our loop of current is going to look something like this. It's going to lie on the xy axis. Okay, and it's going to have a certain radius of d. Right, and then we're interested in some point r away, some point distance r away, right? And the key thing, by the way, in studying dipole is that the same way we did for electrostatics, we will assume that r, the distance from the point, is much larger than d. Otherwise, we'll get we cannot simplify the result. Okay, so we have a bunch of, so this is, the current is flowing this way in the dipole, call it I. We have one element here, dl prime, right? Then we have r hat, and then we have r, and then the distance between an element on the loop, and the point is going to be r minus r hat. Okay, and we said we're using spherical coordinates. So in that case, dl prime is going to be d phi hat, right? Because we are constrained to move on a circle. Okay, so let's examine the kind of field that would. Oh, by the way, what we want to solve for here, we can do the Biot-Savart law, but we want to solve for A, because solving for A will be easier. A will always match the direction of dl prime, right? This will be in the same direction as dl prime, so it will be easier to solve for. And then after we find A, we can just find B by taking the curl of A. Okay, and the other thing is, when we're calculating A in spherical coordinates, is A going to depend on phi, on which phi angle we are at? So this point has the coordinates r, phi, theta, right? And we know what theta is in like this is theta, right? So is it going to depend on phi? No, it's not, because from the symmetry of the problem, right? Because if I rotate this loop of current, I will get the same field. The problem is symmetrical such that the calculation of A does not depend on the angle phi. Okay, let's look at this loop head on. So this is the loop, and this is my point, right? And then this is where phi prime equals 0, right? And this is where phi equals pi over 2, right? This is the x direction, y direction, and then the z direction is going up, right? And this is where phi equals minus pi over 2. Okay, so we want to examine what happens. Let's say I have an element here, dl prime element here, right? So let's call it dl, this element I dl1. Okay, so this element is in this direction. So we said the A field will always have the same direction as the element. That's why we went to the vector potential, because it's simpler in that sense. The component, the component of A that is due to this element here is going to be dA1, and it's going to have the same direction as this element. This element has a mirror element here, right? That's in this direction. So let's call this IDL prime 2, right? So this will give me a component, an infinitesimal component of dA at that point that's in this direction, right? And every element here on the loop is going to have its mirror element. Like the element here is going to have the mirror element there. The point is that, notice those two elements, if we like find their components, the horizontal components cancel out always, and the vertical components add up. So essentially the field will always be in this direction, right? And all we need to do, we don't need to integrate across the whole loop. All we have to do is integrate over half the loop, right? And then multiply by 2 to get the effect of summing up two components, right? So this lets me write A, this, okay? And A is always going to be in the direction of phi hat from the symmetry, right? So A is always going to be phi hat, right? It doesn't matter where I am, where the point is. The A is always going to be pointing in the same direction as dl prime, and dl prime will always be pointing in the direction of phi hat, right? So I'll just apply the Biot-Savart law what is the Biot-Savart law in terms of the A vector? When we know it's mu naught I over 4 pi integration of the loop dl hat over r minus r prime, right? So using this Biot-Savart law written in terms of the vector potential, I can write A equals phi hat mu naught I over 4 pi, and then I need to integrate the loop from minus pi over 2 to pi over 2. Oh, by the way, I forgot to do something here. So this element here is going to be, is going to be, so this is r prime, right? It's going to be at an angle phi hat, right? Sorry, phi not hat, phi prime, right? It's on the loop, right? So that tells me that this angle is going to be also phi hat, right? Sorry, phi prime. Why is that? Well, right. So to show that this phi hat here is equal to this phi hat here. Let me erase those arrows. I don't want to get my diagram too crowded. So let's zoom in here actually. So let me, so this is the center. This is the circle, right? This is the element. So this angle now, let's take the tangent, right? The element is in this direction, right? And then, so this is phi here, right? And this is 90 degrees. So this angle here, this angle plus 90 degrees is going to equal phi, right? Well, this is also 90 degrees, right? Because this line here is normal to the circle. So also I can look at this angle and say this angle plus 90 degrees, right, should also, plus this angle should also equal 180 degrees, right? So that's the main, that's right, so I extend this here, right? So those three angles, 1, 2, 3 should equal 180 degrees. And also those two angles, 1, 2 prime, 3 prime should equal also 180 degrees. So from that consideration, 1 plus 2 prime equals, 1 plus 2 prime is phi away from 180 degrees. Also 1 plus 2 is phi away, is some angle away from 180 degrees. Since 2 is 90 degrees and 2 prime is 90 degrees, 3 has to be equal to phi. It's a geometrical argument, right? So that tells me that the angle here is going to be phi prime. Okay, so the point of all of this is that when we want to apply the Biot-Savart law, we don't care about the field in the general direction. Because we know that the vertical component is what will remain. We know that the horizontal components are going to cancel out from the symmetry. So we need to get only the vertical components. So we need to multiply by sine phi prime. So I end up with what? I end up with, so I apply that law, right? So I end up with sine phi prime d. There's a d, by the way. I need to apply this. Instead of dl, I need to apply d phi hat, right? So that's where phi hat comes from. And then I have d phi. So there's a d here. D is constant. And then I have d phi prime. D phi prime. I applied this thing, the linear element. and this is a vector, of course. Okay, over r minus r prime magnitude, Weber per meter. And now I can evaluate this integral. To evaluate this integral, I have to find r minus r prime, of course, right? And I can use this formula. So I know that the magnitude of a vector is just the dot product of that vector square root. So we know this identity from vector algebra. So I can write this as magnitude r minus r prime dot r minus r prime, and just apply the distributive law. So I end up with r dot r plus r prime dot r prime minus 2r dot r prime. Okay, r dot r is just r squared. R prime dot r prime is just d squared, right? The distance from the origin to the element on the loop is just d. The radius is d. And this one is a little bit more tricky. What would this be? So we said we can make phi here anything we want. Because we want to make phi anything we want and we'll get the same result. Doesn't matter. Let's make phi 90 degrees, pi over 2. Right? So if I make phi 90 degrees, I can, right? So let me draw the coordinates again. So this would be r, right? At 90 degrees, it's within the z y axis, and then I want to dot it with some vector that's on the loop, that's pointing the loop r prime. Right? So I assume that it's at 90 degrees to simplify because it doesn't feed. It's not a function of phi anyway, right? So I can then take. So this is theta. I can. What happens when you dot two vectors together? It's a projection of one vector on the other. So I can decompose r into a component that's in the y direction. This has magnitude r sine theta. So this is r cosine theta, and this is r sine theta, right? And this component, the normal component r cosine theta, is not gonna be part of the dot product because it's 90 degrees with respect to r prime, right? So this anyway cancels out, right? And then I need to project r prime into r sine theta, right? What's that? That's again the projection here is going to be r prime, the magnitude. What's the magnitude of r prime? It's d, right? And this is now phi prime, right? It's going to be d sine phi prime. Okay, so the projection is going to be this times this. So r dot r prime is going to be rd sine theta sine phi prime. So now I can write my A as phi hat. And this is a very general argument. I mean, I assumed that phi is at pi over 2. That does not make the result less general because the result anyway does not ultimately will not depend on phi, right? We know that. So mu naught I d over 2 pi integral from minus pi over 2 to pi over 2 sine phi prime d phi prime over square root r squared plus d squared minus 2r d sine theta sine phi prime. Okay, now we want to apply the binomial theorem to simplify. Right, and this is a similar exercise to what we've done in electrostatics, where this integral is really hard to do, and anyway it's useless to try to do an analytical result. It doesn't give you any physical insight to try to integrate this directly without some simplification. I mean, to verify that, I tried to, right? So let me open this up. So I went to Mathematica and I tried to integrate that expression directly. I mean, all I did now is I took r out from under the square root, and I just tried to get the analytical result, and this is the analytical result. Notice how it continues and continues and continues and continues. This is ridiculous, right? So you can see, like, the reason for this approximation is that we want to gain some physical insight, and just blindly doing the mathematics is not going to give us any physical insight. So, right? Now, in contrast with the solution that we get after we simplify. So let me take that out. Okay, so we want to apply the binomial theorem to simplify this expression to get something that is easier to integrate, that will give us physical insight, right? And because remember, all we care about is get some reasonably physical form for the solution that makes physical sense. All we care about, as we said, is the field at some distance, some point that's farther away from the loop, such that really the internals of the loop don't matter anymore. We just want to look at the net field coming out at a large distance away from the loop. So that's where the simplification comes from, R being much larger than D. Okay, so how do we apply the binomial theorem? Well, let's start with 1 over square root. Well, the first thing we said is R much larger than D, so we can drop the D square. So I end up with R squared minus 2RD sine theta sine phi prime, right? And I can take R out. What happens if I take R out? So let's say put this R squared over R, and then I take R squared out. So I end up with 1. R squared square root gives me R, right? So this is my simplification. And then, so this is equal, this is the simplification now. This is equal to 1 minus 2 d over R sine theta sine phi prime power minus half over R. Okay, now here d over R is much less than 1. So we can apply the binomial approximation here, where 1 plus x to the power p equals 1 plus, approximately equals 1 plus px if x is much less than 1, right? Because d of R over R is much less than 1, this whole term here is much less than 1. So I can say that my 1 over square root, I won't write the whole thing, is approximately equal to 1 plus, what's p in this case? P is minus half, right? So I end up with minus half x. What's x in this case? X is this term. So this is already has a minus sign in it. So the minus goes away, becomes plus. And then I have 2d over r. So 2 cancels with 2. I end up with d over r sine theta sine phi prime over r. Okay, now we can plug this into the integral to evaluate. So remember we had A equals phi hat mu naught I d over 2 pi, and then we have the integral that we wanted to evaluate. So all we have to do now is we now have to integrate this, find the indefinite integral, and then evaluate it from starting from minus pi over 2 ending at pi over 2. So this is easy to integrate, and I won't do the integration. I'll just go back to Mathematica and show you the result. So this is the integration of this expression, and we get this result here. Phi p is just phi prime. So whenever you say p, you see p is just prime, right? So phi p is phi prime. Okay. So I'm taking this now, and I'm integrating this. This is the result. This is the integral. This is the indefinite integral. So I'm evaluating it from minus pi to pi. So the endpoints are minus pi to pi. Well, let's look at the terms. What's cosine pi over 2? Sorry, the endpoints are minus pi over 2 to pi over 2. What's cosine pi over 2 and minus pi over 2? 0, right? So this term at the end goes away. It doesn't matter. What's sine 2 phi prime, right? What's when I put in pi over 2 times 2, I end up with pi. So what's sine pi and sine minus pi? Again, 0. So those last two terms don't show up in the equation. We end up with just this, the first term showing up, right? And I have sine theta, and then I have phi p, which is pi over 2 and minus pi over 2, right? So it's d phi p sine theta over 2r squared. So when I apply it over the endpoints, d, instead of phi prime, I put pi over 2. That's the first endpoint. Sine theta over 2r squared minus d minus pi over 2 sine theta over 2r squared. Minus goes with the minus here, becomes plus. I end up with 2d pi over 2 blah blah blah. So I end up with the 2 cancels out, right? And then and the pi cancels out. The 2 cancels out, and the pi cancels out. So I end up with, let me write this. So this is going to be phi u naught I d over 2 pi. So this is going to be d pi sine theta over 2r squared. Right, there will be a 2 that's cancelled out with the 2 in the denominator, and then the pi over 2 has a 2 in it, which shows up there. So notice the pi cancels with the pi. So I end up with A being phi hat mu naught I d squared, d and d comes d squared, sine theta over 4r squared Weber per meter. And this is the approximated. This is approximate, of course, but it's a very good approximation as R gets much larger than D. Okay, so this is the magnetic vector potential for the magnetic dipole. What's the magnetic field? It's just going to be the curl of A, right? I mean, that's how we get from A to B. Our end goal is B, is the magnetic field due to the dipole. So if we recall, since A is not a function, not function of phi, that kind of simplifies the curl a little bit. So I don't have to write the whole curl. I'll just write, because anything where I have dA phi by something else, it goes to 0, right? So the curl of A, if I cancel out everything that goes to 0, is going to be 1 over r sine theta. And this is something you get from the textbook or from the tables or whatever. You know, you don't have to memorize this. You have to understand it at the beginning, but then you don't have to memorize it all the time. You know? Just have to know how to derive it if you end up in a desert island where you don't have the textbook with you. Sine theta r hat minus 1 over r d over dr. So this is with everything that's 0 removed. Right? This is the curl and spherical coordinates where everything that evaluates to 0 is just removed to simplify. Okay, and that's it. We just now, so I have 1 over r sine theta. So I take Fe. What's Fe? And I mean, this is Fe, right? Fe times sine theta, I end up with sine squared, and I derive it with respect to theta. So I end up with what's Fe? Mu naught I d squared over 2r squared, and then I differentiate the sine squared. So the sine squared is going to be, sine squared is going to be is that correct, by the way? Oh yeah, 4. Sorry, 4r squared. Sine squared is going to be 2 sine theta cosine theta. That's how you differentiate sine squared, right? Right, and 2 cancels the 4 here. This becomes 2. Right, minus, computer is a little laggy, minus 1 over r u naught I d squared over 4r squared. So it's r Fe, right? So r Fe is going to be 4r. The r cancels one of the r squared, and then we differentiate this. I need to differentiate this with respect to r, right? So 1 over r differentiated with respect to r gives me 1 minus 1 over r squared. And this is theta hat. Right? Simplifying matters, taking out all the common terms. Oh, by the way, here, sine theta cancels sine theta here, in this term, and then removing everything, u naught I d squared. Let me make sure my computer doesn't die. Okay, mu naught I d squared over 4. So the common elements are mu naught I d squared, and then I have 2. I have 2r squared, r cubed, and then here I have 4r cubed in the other term. So I need to make those match. So I multiply by 2. I end up 4 with 4, and I multiply by 2 here, just to make the denominators match. So I end up with 4r cubed on the denominators, common denominator between the two terms, some terms, and then mu I d squared. I take that out, or the minus cancels with the minus. This becomes a plus. I missed something here. Oh, there's a sine theta here. Sine theta. I forgot about that. So I end up with this simplified equation. Cosine theta r hat plus sine theta phi theta hat. And this is the magnetic flux density due to the dipole. Notice it's not a function of phi, it's only a function of theta and r. It's a function of how far you are from the dipole and at what angle. So this is the dipole. It's a function of how far you are from the dipole, r, and it's kind of like the electrical dipole where it's proportional to 1 over r cubed. And it's also a function of the angle with respect to the dipole. Whether you are at this angle theta or at a larger angle, you have a different reading on the dipole field. Right, so this is a nice result. Let's compare that with the result that we got for electrical dipoles. For electrical dipoles, we got E equals P, where P is the magnitude of the dipole moment. So remember P, the dipole moment was QD, where D is a vector, the distance between the two charges, right? So it has units of Coulomb meter, right? Over 4 pi epsilon naught r cubed. And this is the result that we got for the electrical dipole, by the way. I'm just repeating it. 2 cosine theta. I'm going to show you that it's exactly the same. Sine theta. And then the field due to the magnetic dipole is going to be, what is it? Is mu naught I d square, we just calculated it, over 4 r cubed r hat 2 cosine theta plus theta hat sine theta. It is the same thing. I mean, this constant here has a different form slightly. Let's make it match more, like more precisely. So how do I do that? Let me add, what, I won't change anything if I multiply this by pi. So I have 4 pi r cubed, and then put a pi up here, pi d squared, right? And then let me take this to the bottom. So I end up with 1 over mu naught r cubed, right? Now it's more symmetrical, right? So this suggests that there's an analog to the dipole moment in electrostatics, which is the magnetic moment in magnetostatics, and it turns out to be this term. It turns out to be, this is the magnitude of it, the magnetic moment. This is the magnetic moment, which is the analog, just from looking at the mathematics, it's the analog of the electrical moment, electrical dipole moment. So the magnitude of the magnetic dipole moment turns out to be just I, the current of the dipole, times the surface area of the loop, right? What's pi d squared? This is d. It's the pi r squared, of course, is the area of the circle. So it is the area of the dipole. So it seems just taking the current times the area of the loop gives me the magnetic moment, the magnetic dipole moment. So this is called the magnetic dipole moment, right? So that's interesting. Of course, the dipole has direction, electrical dipole. In a similar manner, the magnetic dipole has a direction. What's the direction? The direction is just the orientation of the surface area, right? So this is the dipole. The orientation of the surface area using the right-hand rule is the direction of the orientation of the area of the loop is the direction of the magnetic dipole. Can be defined as the direction of the magnetic dipole. So if we take the analogy, we have two charges, Q plus and Q minus, with D between them, right? And then P equals QD, right? The analogy here is that it turns out for the loop, the magnetic dipole due to the current loop, is M is going to be pointing in this direction, and its magnitude is just going to be equal to I times ds. Or we could write it, so we can write it like this, or we can write it as I times the surface area of the area enclosed within the loop is going to be pi d squared. This is d, and then n hat. So it is a vector. The dipole, the magnetic dipole moment is a vector, right? So we can rewrite B as mu naught. What was B here? So this is I pi d squared. We said we can write it as m. I can put mu naught back up. So I end up with mu naught m 4 pi r cubed r hat 2 cosine theta plus theta hat sine theta, right? So I'm just rewriting, not doing anything fancy. I'm just rewriting B and A using this redefined constant, which is the magnetic dipole moment, which is equal to I pi d squared, right? And I can rewrite A. We found A previously, right? So it was equal to mu naught I d squared sine theta over 4 r squared phi hat, right? So I just need to add pi here and pi here, and I end up with m. So this is m over 4 pi r hat. Okay, so interesting thing here, we have m, and then we have a magnitude of one vector, and then we have the unit vector in the phi hat direction, and then we have sine theta. What should occur to your mind whenever you see a sign? What should occur to you is that there is some kind of cross product, right? So this is the dipole, and this is some distance, and then this is r, right? And then phi is always going to be perpendicular to r, right? But phi hat is always going to be perpendicular to r, but also phi hat is always going to be perpendicular to m. We defined m to point to be the orientation of the area of the dipole, right? Because phi is going to be always perpendicular to r and m, and there's a sine theta here in the expression. Theta is the angle between m and m is a vector here. Theta is the angle between m and r. That tells me that phi hat should arise as some sort of cross product, right? So what is it? It is this form. It's going to be mu m cross r hat, right? So this, what is the vector that's perpendicular to both m and r, or r hat? R hat is this one here. It's in the same direction as r. So what is the vector that's perpendicular to both m and r hat? That's phi hat. It's perpendicular to both, right? And what is m cross r hat? It's going to be sine theta, the angle between m and r, and times the magnitude of phi hat, which is 1, right? Times the magnitude of m. So m cross r hat is going to give me m magnitude phi hat sine theta. Right? It's going to give me m magnitude, the magnitude of r hat, which is 1, and then sine theta, and then it's a vector, so the direction of that vector is going to be phi hat. So this is the simplified expression. This is, of course, approximate, using the binomial approximation, which is a very accurate approximation for r much larger than d. So this is the formula for the magnetic vector potential for a magnetic dipole, right? And it has units of Weber per meter. Okay. This concludes the discussion about the dynamic magnetic dipole, at least mathematically. One interesting thing about the dipole, though, and I want to mention as a closing point. So we know that the dipole moment for electrostatics was QD. It had units of Coulomb meter, right? And then when we take it in space and take a distribution of dipoles in space. So there's a dipole density in space. So we take Coulomb meter divided by meter cubed, right, to find the density of the dipole moments. I end up with Coulomb over meter squared. I get the same unit as the d vector, which is the flux density. So that led us to say that the flux density is, in a way, describes like dipoles in free space. So polarization and the flux density are really the same thing. If we look at the unit for m, what is m? Pi I squared, I pi d squared. It has units of amp meter squared, right? What happens if I take the density? I imagine in space I have in a volume an infinite amount of dipoles like that. So I take the density of a dipole in the region of space. So I take infinite amount of dipoles, each with a unit, sum them up, each with a unit amp meter cube squared, divided by m cubed to get a density. What unit arises when I do that? The unit that arises is amp over meter. Notice the slight difference here. The unit that arises is the same unit as the H field. The H field has amp per meter. So this tells me that when I represent the dipole as a loop, the dipole really is another representation. It gives me the dipole density, the magnetic dipole density turns out to be something that has the same units as the H field, as the magnetic field intensity. So the magnetic dipole density, as those looked at as those current loops everywhere in space, is another way of representing the H field, right? And we will, in the same way we match the P field to the D field to get the total D field, we'll also now match the dipole moment density, magnetic dipole moment density with the H field to get the combined field and define not the permeability of free space, but the general permeability of any material. Right? So we will use a very similar argument, and it's curious that when you look at dipoles that are charges that with a distance between them, you get something akin to a flux density. The unit match the flux density, but if you model the dipole as a loop, you get something again akin. You get something that has the same units as a field intensity. Yeah, and you have to get those same units because that's how you link this model back into the postulates of electrostatics and electromagnetics. We will discuss that further next, but we will end here. We will stop here. All right. Thank you, guys.